Good morning. Welcome to Krishna's classroom. We continue from where we left last time, and what we intend to do today is to look at some results which come out of applications of Holder's inequality. And that they are, they give some insight into the structure of LP spaces. Okay. So that's the advantage that you have. Okay, so let us start working on this. So we write this as a corollary. It's a corollary to the previous results. Let E be a measurable set, and let 1 less than p less than p. Suppose P are 0 is defined by all AF belonging to LPE such that the P norm of F is less than. It's a ball of radius capital R with center at the origin in the normed linear space LPE. Okay, comma, so let's just write that the ball, like the closed ball, radius R at the origin in the normed linear space then the family LPE is uniformly integrable over E. So let us give the proof of this result. So what we have to prove is this. We have to show that For every epsilon positive, there exists a delta positive such that for any f belonging to PR0, integral over A is less than epsilon if A contained in V is measurable and is such that measure of the Lebesgue measure of A is less than. So this is what we have to prove. We have to show that for every epsilon positive there exists a delta such that for any f belonging to PR0, f is integrable or and more precisely the integral over A of mod f is less than epsilon if A is a measurable subset of E with a measure of A less than delta. This is true for every f belonging to. So it is uniformly. So the class BR0 is uniformly there. So that is the definition that we have to prove. Okay. So this is the result that we have. Okay. So let A be a measurable subset of E. Of finite measure. Of course, we are not assuming E is a finite measure. Okay, but we are looking at subsets, measurable subsets of E with finite measure. Now we consider this one. LPA and LP. Where Q denotes the conjugate of P, the usual notation. Where Q is the conjugate of that is 1 by P plus 1 by Q equal to 1. Suppose P lies between 1 and infinity, therefore Q also lies between 1 and infinity. Now the relative position of P and Q is the following. See, when P equal to 2, you get Q equal to 2. So you see, on the line, suppose this is 1 to infinity, and this is 2. Then if you have P over here, then the corresponding Q is somewhere. Okay. On the other hand, if P is here, then Q is here. So P lies between 1 and 2 implies Q lies between 2 to infinity. And that is quite obvious. And when P equal to 2, then you have Q also equal to 2. Okay, and that has some significance. And you see that I was making a mention that L2 is a pre-Hilbert space. Okay, so it is the Euclidean structure. That is the, or what you call, a unitary space. Now that is something that we have here. That is something very special. Okay, and there is a lot of results connecting LP and LQ. Okay, and if for LP, LQ becomes the so-called dual space, but that is not our concern at the moment. Okay. Now define equal to what on A. Since measure of A is finite, that is very obvious. Now applying Holder's inequality, to F and C, we have the following estimate. And what is that we want to estimate? We want to estimate this integral over A mod F. This is what we want to estimate. And this I can rewrite as integral over A mod F into G, because G is identically equal to 1 on A, and this by Holder's, you have this is Holder's inequality. Now we know specifically what your G is, and we shall make it up. So we have got an estimate of this inequality. Now what you have is, now for every F belonging to PR0 0 is less than or equal to integral over E 1 by B, and this is less than or equal to, that is by the choice of, that is F belongs to PR0. Okay, because we have assumed that this is bounded by M, sorry, what we have said, we said that this is bounded by R is the bound. Okay. Okay. Therefore, what we get is this. Further, integral over A is equal to measure of, because G is identically equal to 1 on this. Therefore, this implies every F belonging to 0, PR0, we have integral over A mod F is less than or equal to, we use this inequality and plug in these values there. So you get M, not M, actually R into measure of A this is 1. Okay. So this is the estimate that you get. Okay. Now we can adjust. What do you want? You are going to take a measure of, you want to make this less than epsilon. Okay. So therefore, which implies for each epsilon positive, there exists delta equal to epsilon divided by R Q So what we get is this. So for each epsilon positive, there exists, if we define delta equal to this, then integral over A then for A less than delta, what we have is this. So this is the delta value that, so given epsilon, there exists a delta and this delta is complete. So this is a very nice estimate of the integral of f. What is important is that every function is in this particular ball. It's a bounded ball. Okay, it's a bounded ball with radius r. You see that for all the elements f belonging to this BR 0, you see that this estimate holds. Whenever A has measure less than delta, then integral over A mod f is less than or equal to epsilon. Okay, where delta is calculated in terms of epsilon and r and q in this way. So that completes the proof of this theorem. So that's one result. A second corollary that we want to look at is the following. Let E be a real line of finite dimension. Let 1 let P1 and P2 be such that P1 is less than P2 and both lie between 1 and okay. Then in short, it simply says that this as P2 becomes larger and larger, LP1 or this set LP2 is contained in LP1, which means it shrinks. Okay, so that's the statement that we have. What we have is this. Let's place these numbers now. what we have is this 1. Then you take P1 to be less than P2, and this there is possible equality also. So we are considering the set that means we are also talking about L1 and L infinity in this context. Now let us give an estimate of this. Moreover, where we have the estimates for this constant, C is equal to measure of now C is equal to measure of E when so this ratio is actually 1 by P1 minus 1 by P2. Okay, so if we let P2 to go closer to infinity, as P2 tends to infinity, what happens? The second goes and you get 1 by P. So that's the estimated. Okay, but we have separately. Now let us give the proof. So let's have a sort of feeling for this. These sets. Now let us have a feeling for this. What it says is the following. The main statement of the theorem is that LP2E is contained in LP1, and the condition that you give is the following. P1 less than. Okay. One can just get a feeling for this result by taking some bounded interval of the real line. Okay, so you take E to be, for instance, you take E to interval 0. Then measure of E is like that. Now, what this theorem says is the following. That means that what is so you are now comparing LP1 and so this is the sort of inequality that one gets here. LP2 is contained in LP1 over the interval 0. Now this is quite easy to check. Okay, right? Now we shall prove this result. You can even take some specific values like P1 less than P2. So you take P1 equal to 1, P2 equal to okay. So P1 is less than P2. So what you get would be L1 L2E is what you get in this case will be L2E and let us examine this particular thing. Is it a proper containment? Now you see that you take x to the power alpha. Okay, and we have so when is this integral 0 to 1 x to the power alpha is finite. This is when f belonging to now f belonging to finite. Now these are the two statements that you have, that is so compare these two. and the problem could arise in the neighborhood of 0. Okay, so let us easily resolve this. When is this finite? So you should have, see what is the integral of this. You have x to the power alpha plus 1 divided by alpha plus 1. Okay, and alpha plus 1 suppose alpha plus 1, I am leaving alpha to be any number. Alpha plus 1 is greater than minus 1. Then this will become finite. So it's greater than minus 1. So alpha is greater than minus 1. This is the condition. Whereas if you work with this, you get 2 alpha greater than minus. Now compare these. So that means this is alpha is greater than. Okay. So this is what you have in L2. This is what you have in L1. Okay. So you can easily check that alpha greater than minus 1, alpha greater than minus 2, or sorry, minus 1 implies minus 2. Okay. So let us, so that is where the singularity appears here. See that if alpha is equal to minus 1, then what happens is that this is going to be is if alpha is less than minus 1, we can write here minus 2. Okay, when alpha is actually less than minus 1, this would become, the index would become negative. So you get 1 by x coming here, and the limit at value at 0 would become infinite. That's the problem. So here the corresponding interpretation. Now what does this mean? What does this mean? So alpha greater than or equal to minus 1 means f belonging to L1, and alpha greater than or equal to minus 2 means alpha x to the power f belonging to L2. Okay, so you have now f belonging to L2 implies f belonging to L1. Okay, so that's the sort of example that you can look at. So let us now prove this. P2 is finite. So P2 equal to infinity we will consider later. Now define define E equal P1, and this is certainly greater than P1 implies this. This is greater than 1, and conjugate is 1 by P plus let so you can easily work this out, this relation, and if G belongs to the characteristic function of E, then right. It's always better to take an example, get a feeling for what the result is all about, and then work on this. Now, I think I want to make some comment on this function x to the power alpha at the end of this proof. So, applying inequality, we have integral over E G is identically equal to 1 on E, and this is less than or equal to E1. Just the definition. That is just an application of the Holder's inequality. And this is equal to norm of the P2 norm of F raised to the power P1 into measure of E. Let's estimate that. Then that is the norm of this. Okay, this is norm P1 is less than or equal to norm of P2. So we are taking 1 by P1 power of this. So this is this one times measure of E 1 by QP1. Now 1 by QP1 equal to okay. So this is a very simple computation that you have. Okay. So which implies that norm of C times norm of E2, where C is equal to measure of E P1. And what is that? 1 by QP1, which is equal to measure of E P2 minus P1. So that completes the proof. Yeah. Now what we take up is the case where P2 is equal to infinity. Now case and P1. So we will estimate this. Now integral over E which is less than or equal to F P1 subnorm of that to measure of E by applying Older's law. Okay, and that gives norm of F P1 is less than or equal to infinity into that is P2 into where C is equal to measure of so we completed the proof of that. We just give an example, the type of function that we have handled earlier. That means x to the power alpha. Now you see that, you look at the graph of this function. It is nice to know the behavior of x to the power alpha in the neighborhood of 0 and infinity. We take okay. Let us take the function e to be and take alpha. Alpha could be any real number. Now let us look at the graph of this. We split this into two portions when alpha equal to 0 and alpha is greater than or equal to 0. Then what happens is the graph of this function becomes 0. Suppose, okay, let us take alpha greater than 0. If alpha is greater than 0, then this function is something like this. I mean, it depends on alpha, what it is. So as alpha goes to infinity, what happens? This function will become bounded. So x to the power alpha, sorry, it will just start coming down. So you see that these are the type of we are actually interested in nature of this function. So you see that now we take alpha to be, if alpha is equal to 0, then fx is equal to 1. This is alpha is 0. Now alpha greater than 0 is going to be 0 and this is going to be 1 to the power whatever be the alpha, so it is going to be something like this. This is alpha greater than 0. And when alpha equal to infinity, it is going to be a sort of discontinuous function. Because if this is going to be this, and at 0, this is the function. We will mark it out in the color. This is the case where alpha equal to infinity. So this is the case where alpha is greater than 0 and it will vary from no, the angle would, or the, but it's a function that goes monotonically, and it's identically one function when alpha equals 0. Now, what happens when alpha is, so this is alpha equal to 0, when you have alpha less than 0. When alpha is less than 0, see, you are getting a function which goes, and at 1 it is going to be 1, and the function would take the graph something. Okay. Therefore, the integrability problem would arise. In all these cases, the integrability problem does not arise. Okay. And when does the actual problem arise? You see that when alpha equal to -1. Okay, so you have alpha lying in this itself, -1, -1, when alpha is less than -1, what happens to the integral x to the power alpha? X to the power alpha would become area enclosed will become infinite. But in between -1 to 0, you see that although the function grows to infinity as x tends to 0, nevertheless, the integral that you get would be finite. So these are the, so this is x to the power for various values of alpha less than 0. And the turning point is alpha equal to -1. There the problem starts. Okay. So now this knowledge is really worth looking at. You should make a similar study of x to the power alpha over the interval 0 to infinity. When alpha is positive. As alpha becomes large. Okay. And that sort of the order estimates as x tends to infinity and as x tends to 0 of x to the power alpha, and the integral is now investigate integrability of x to the power alpha on zero to infinity that is determined in relation to And this is a worthwhile study on this kind of function. So that means we will be looking at integral 0 to 1 and integral 1 to infinity. These two integrals, when are they finite? For what values? This is a very good, study and very useful in constructing worthwhile examples. I just given a glimpse of what it looks like, but in the nutshell, this is the problem. Alpha 15 a real number. So we look at the following example. Take a measure of finite and let 1 E1 infinity. Then LP2 E is a proper subspace of that means you have LP2 this is a claim that you are doing. Okay, so you take this one, let take fx x to the power alpha where 1 upon P1 so this is what you can prove, right? So essentially you will be working on this kind of integrals. Okay, thank you very much. So we stop here. And now our path is clear that we are going to pursue the completeness of